In this video, I'm going to give an introduction to digital control. We're then going to focus on the sample data control system. So the content of this short lecture is as follows. I'm going to go through the advancements in digital computing, the form of the digital control system, so in practice, and then we'll then move on to sample data control system, which is used for theory and simulation. So after this lecture, you should be able to understand the positives and negatives of digital control over that of analog control, understand the form of a digital control system, i.e. inputs, so from sensors, control algorithm, and then outputs, the actuators, and understand the form of the sampled data control system in key features such as the sample switch and also the zero order hold. So advancements in digital computing. So you're all aware perhaps of Moore's law. So it's the observation of the number of transistors in a dense integrated circuit doubles about every 2 years. So this means that computers, microprocessors, microcontrollers have become a lot more powerful as time's gone on, especially in the last 20 years. And this has meant now that we can do a lot more kind of advanced control because we have a lot more power. So we can run kind of quite advanced, quite lengthy control algorithms or algorithms on board a computer. So we can undertake these calculations in reasonable time. Whereas perhaps 20 years ago, you wouldn't have even considered, for example, an autonomous vehicle being controlled via a computer. And you can see the Tesla processor there. Sorry. So you can see the Tesla processor there. 20 years ago, you wouldn't have dreamed of the amount of transistors that you can put into that circuit, and the amount of calculations that you can undertake in a very, very short time. Okay, and that's the reason why one of the main reasons we moved to digital is you can undertake calculations very, very quickly now. So in terms of the timeline, Alan Turing, you're probably all aware of him, considered the father of computer science, theoretical computer science, and also artificial intelligence. I guarantee you've all heard of artificial intelligence. So yeah, advancements in digital computing has meant that we're at this point now whereby there's a lot of kind of advancements going on in the world, such as manufacturing, autonomous vehicles, autonomous systems, robotics. And the advancements in digital computing, the positives, digital controller, it's insensitive to environment, example temperature and drift. Whereas if you look at a negative in an analog controller, it suffers from drift due to temperature change and aging. Okay, so that's a big advantage with digital control. Digital control, it's easy to implement changes. For example, because it's programmable, you effectively implement it via an algorithm, and it gives us predictable behavior. Advanced control possible because we're implementing it via an algorithm. We can do a lot more advanced control, so predictive control, self-tuning control, nonlinear control, and you can also perform multiple loops within that control algorithm. So negatives of the analog components have tolerances. So because it's an analog controller, it's the amplifiers for example the PID, for the proportional integral derivative, the amplifiers used for that, and the circuits are made up of electronic components. They all come with tolerances. Components are hardwired. So it's not as flexible. For example, for a digital controller, if you're implementing a PID, the proportional, the integral, and the derivative gains would just be numbers on the algorithm. Within the analog control circuit, it would be physically hardwired. So it's not as easy to change. In the digital, I'd just be literally just changing a number and then uploading the algorithm to the microcontroller. Limited to classical control theory. So I said here you can do some lot more advanced. So you're limited very much to the classical continuous time theory, and the parts tend to be large. So in terms of analog control, though, it does come with some positives. You've got a high bandwidth and a high resolution because the amount of data, because you're looking at a continuous signal. So you've got a lot of information there, a lot of data. It's easy to understand and implement, relatively easy to understand and implement, and relatively low cost. But digital control now tends to be very, very cheap. Like you can get an Arduino Uno for just under £20, a few electronic components, and you can build yourself a control system for very, very cheap now. So the negatives of digital control. So because, and we're going to come on to this, But in digital control, because computers work in discrete time events, we're effectively sampling the continuous time signal. Every sample interval, which I've denoted here, T subscript S denotes a sample interval. So we effectively sample, okay, and that'll become more clear. There's pulse width modulation and resolution limits. Again, some of these points are going to get a bit confusing, but when we move on to the short lectures in embedded control, some of this will make a little bit more sense. It says resolution limits, and you have things such as numerical problems such as rounding, analog to digital converter and digital to analog converter boundaries, i.e. the resolution, speed and cost. Again, we'll talk more about when you get onto the embedded control, and the central processing unit perhaps could have performance limitations. So in terms of advancements, I spoke briefly, robotics, autonomous vehicles. So I've got here some free videos. I'm not going to play these videos because what you can do is you can just go into YouTube and go into search and just type in these names here and you'll find these videos. So this one, we've just got an autonomous vehicle, a Tesla, that's effectively just doing displacement control. Got here a self-balancing robot that's keeping itself upright, and it's also using a camera to follow a given person. And then Boston Dynamics robot doing kind of some gymnastic routine. So the advancements in computing, the advancements in digital computing has enabled these products to be developed. Okay, for example, the autonomous vehicle with an analog controller, you probably wouldn't have dreamed of it because the environment changes so much. And hence, if you use an analog controller, it's made up of hardwired of electronic components, and it suffers some temperature drift. Okay, it's not probably going to perform too well, and probably likewise for all the different examples that I've got on the screen here. So in form of a digital control system, so in practice, it's relatively simple, really. There's three main components that you need to get yourself really aware of. So the use of a sensor here, and I'm going to say this enables you to see what's going on in terms of the state of your system. And what we've got here is a microcontroller. So the information from the sensor is the input to the microcontroller. Okay, so what's going on in terms of here is your input and information. You're effectively telling the controller or informing the controller of some form of physical phenomenon. In the case of this, what we're looking at is a fluid level control system. So we're looking at controlling the level of this tank. So we could denote this H, and obviously you can see that water is also flowing out of here, and we're trying to control. So what we've got here is a level sensor. It's effectively measuring the height of the water tank, and we're going to obviously in real time you could measure this and provide the information to the controller. You provide the information to the controller every sample point. Then the microcontroller, so the information's going to be processed. It's going to come here at some form of values. Again, we'll talk about this when we get onto the embedded control section. So the numbers, something's going to come in here. It's then going to be a language so that the microcontroller can understand it, and then it's going to take an action. So it's going to say to itself, right, the tank level. I want the tank level to be, I don't know, whatever you want to do. You define a reference. You say maybe I want it to be here, reference. And if it's lower than this, say for example it drops here, the controller then would output here to this pump, which is the actuator, and it would say, right, we need to turn the water supply back on, we need to pump some water from the reservoir, and we need to increase the height of the tank. Okay, so C, I'm going to say the microcontroller, it enables you to think, although it's not in terms of your human brain thinking, because it's all predetermined actions. And then the output here to the pump, which is an actuator, enables you to do. See, think, and do. It's exactly how a human being works. For example, when you're undertaking any task, you're using your sensors on board your body to provide information to your brain. Your brain then is using that information then to take action or to output some form of command along your neuromuscular system to your muscles. Okay, for example, walking. Close your eyes, try walking, closing your eyes, you'll soon collide into something. And there's lots of, obviously you can think of the other senses as well. So it's very much in line and the same sort of idea applies to the human being. So that there is the basis of the control system. So it's being able to see, take action based on what the algorithm that will be on the microcontroller, and then to output an action to the actuator that enables you then to make change. That's all we're effectively trying to do with a control system, is we're trying to regulate something, we're trying to manipulate something to get this desired system performance. And it all comes from the reference. The reference is what we desire. So in terms of a practical control system, what I've got here is, I'm not going to spend very much time on this because this is going to become more kind of it's going to be more explained when we go into embedded control, but I just wanted to take you a step further and to show you that, yeah, something that's actually in practice. So it's similar to what we've seen before. So here you've got a potentiometer, a signal's being inputted to the microcontroller, so it's effectively measuring the angle, because on this particular control system, what we want to do is we want to keep this pendulum angle 0. Okay, you can see here reference. And then the microcontroller is going to have some form of algorithm, which is effectively this. Okay, I should say the sensor bit is here. This is in Simulink. Then you've got the reference. Well, that's going to also be on the microcontroller. And then the output here is to this DC motor. And the DC motor effectively can drive up and down here. So based on, for example, if the pendulum's here, what will happen is the motor will drive this way to bring the pendulum to this position. And if the pendulum is this way, the motor will drive along this here to move it so it's in that position. Okay, and this is just using proportional integral derivative control. So that there is way, way beyond probably where we're at the point now. But when we go on to the embedded control, that is all going to make sense. I just wanted to show you that. So this is if you've ever heard of anti-sway control. And again, we're going to detail this further later. So now if we move on to the sampled data control system. So if we're looking more at theory and simulation now. So we've looked at practice, we've looked at the idea of actuator, sensors, microcontroller. What we're looking at now is a digital to analog converter, because computers are digital and they work in discrete time events. They don't require or they don't work with analog signals. So control algorithm output. So imagine we've got a control action that's coming out of the controller, as we just saw, and it looks like this. So U of k, U subscript k, where k is our basically our sampled control algorithm output, and this is effectively the control output here, 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 and here, and here, and it's being outputted every TS seconds, where TS is our sample interval, and TS seconds, I don't know, we could say we'll just say for ease is 1 second. So every 1 second, a control algorithm output is outputted. What we have is a digital to analog converter, and the one you use is the 0 to hold. And what this 0 to hold does is it effectively holds the control algorithm output for that TS seconds. Think about it in practice. Okay, if you were to just output kind of that point in time a control algorithm output, and that could be, for example, me providing a voltage to a DC motor. Well, what I need to do is I need to hold that voltage for TS seconds, because the DC motor works in continuous time. It's an analog device, so it needs the voltage held for TS seconds. And that effectively is what the 0 to hold does. And you see here U of t, which is our control output, the little star there because it's a staircase. That's effectively what's going on. Control algorithm output, because it's a discrete time, it's a digital device. It works in discrete time events, so you can see these points here, and the motor, because it's an analog device, so we need to use this 0 to hold. And now we've got an analog to digital converter, so the opposite way. So here you've got your analog signal. So this is our measured output. So this would be from the sensor. So this is an analog signal from the sensor, and what we use here is a sample switch to represent a analog to digital converter. So we have our measured output. We have our sampled output, y subscript k, so y of t time domain, y of k, and you can see here our sampled signals every TS seconds. So that hopefully makes sense, and you can see, just to reiterate the notation becomes lowercase u of k. K just represents our sample. So 0 to hold effectively holds a digital signal to convert it into analog, and a sample switch effectively samples a continuous time signal to convert it into a digital signal. So we then move on to the sampled data control system. So this is used to model a digital control system, and this is a mixture of continuous time and discrete time. So it looks very, very similar to what you saw when we looked at the continuous time control system. The only difference you'll notice is you've got a sample switch here, you've got a sample switch here, and you've got a zero to hold here. Right, so let's work our way through. So ideal sensor, as we normally use, just to, in theory, just to simulate, just to simplify things, we just normally assume that's a value of 1. So here we've got our measured output, as you just previously seen. We've got a sampled output, y subscript k. Okay, you've just seen that on the previously. Okay, and what you'll notice here is there's a boundary here and a boundary here, because this here is our continuous part here. So we've got our continuous system, we've got our sensor here, and now we've got this digital microcomputer, and you can see this boundary, and the sample switch sits on the boundary, because what it's doing is converting this continuous time or analog signal to a discrete time or digital signal here. So it's sampling the signal, the continuous signal, every TS seconds. So the amount of information provided to the digital computer very much depends on that sampling interval. Right, then what's happening is we've got a reference. The reference could be external, so it could be like a potentiometer or some external device. However, the reference could also be embedded on the microcomputer, microprocessor. We're sampling that, but like I say, it could be that the reference is external, so it might not necessarily that you need to sample it. So we sample the reference, we then form a sampled error. Okay, so exactly the same way in the continuous time system, we form an error. So the error is just based on, so U of k is just based on R of k, take away Y of k, that's how you form the error. Hopefully you're familiar with that. Then the control algorithm, so that's going to multiply by the control algorithm. It might have some form of discrete time PID, which we're going to go on in a few lectures, in the future lectures time. We're then going to have our control algorithm output, which you can see here is discrete time. And then, as you can see, discrete time signal, the zero to hold then is going to hold that signal for TS seconds. Because as I said to you previously, the actuator, most of the actuators are analog actuators. So you need a continuous time signal. So hopefully that makes sense. So it's this boundary here and here. It's the continuous time and then the computer the discrete time. And it's the idea that you need to sample the continuous time signal because the computer's working in discrete time events. And then you also then need to hold the signal using the zero to hold, which the zero to hold would be in fact located within the microcontroller. You need to hold that signal for TS seconds for your continuous time system. And when we get onto the embedded control, we'll make a little bit more sense in terms of what these values mean. They're effectively going to be, each one of these levels is going to relate to some form of zeros and ones, and it very much depends on the microcontroller, the number of bits that it uses for the analog inputs, and again for the zero hold for the number of bits that it uses for the method known as the pulse width modulation. But again, park that what I've just said. This will make more sense when you get onto the embedded control. And then just an example, what we've used previously. So actual temperature 15 degrees, desired temperature 17 degrees. You form your error based on those. So this is just for one cycle. So you form your error. So in that case, it'd be 2 degrees Celsius. That would then multiply by the control algorithm, output your control algorithm, and then obviously your control action or your control output would go to the heating element. So in this case, obviously the temperature is lower, so it would actually probably increase the power provided to the actuator, and then the process would be the room heating or cooling. And then in terms of the temperature, obviously the sensor would be some form of temperature sensor. So just to kind of reiterate, the temperature sensor is used to see, the actuator enables us to do, and the control algorithm enables us to think. But just don't get that confused with thinking. It's not thinking like a brain. It's not a machine that's got the ability to think for itself. It'll be predetermined actions. So hopefully that makes some sense. I know I haven't gone over the details of how the control system works because I'm expecting that you've got an understanding of that from previous videos. But if you haven't, please see some of my my earlier short lectures where I overview the basis of the feedback control system for a continuous time system. So if you understand the continuous time system, the operation of discrete time or sample data control system is very much the same, other than that we've got the zero hold and the sample switches. So in summary, we've gone over the positives and negatives of digital control over that of analog control. So the massive increase in computer power has enabled us to move on to digital control and digital control systems. The common form of digital control system has been detailed. So the inputs enable us to see, the control algorithm think, and the outputs do. And then the form of the sample data system has been detailed. And the key features, like I just said, sample switch and the zero order hold. So what we're going to do in the next short lecture is we're going to look at the operation of the zero order hold, will be detailed, with a mathematical form detailed in continuous time. What we're then going to do then is we're going to look at the numerator of the continuous time zero hold, and we're going to discretize this. We're going to put it in discrete time form. Which you're probably asking yourself, well, on the previous video, or the previous slide, sorry, it showed that the zero hold was located within the microcontroller. So we'll look at discretizing the numerator. Okay, hopefully you found this video enjoyable. If you've got any questions, please contact me. Thank you.